So today we are going to be looking at inverse functions. We are going to be looking at an inverse function is something that will undo a previous function. And so the x's become the y's and the y's become the x's. So let's look at this first problem. This first problem is just asking us to find the inverse of that relation. And so it's just making us create a table where we reverse the x and the y's. And so what was originally the x's is now going to become the y's, and what was originally the y's is going to become the x's. So the original x's were 0, 2, 3, and 4. So the inverse is going to have those as the y's, and we're going to take the y values and put those as your x's. So it's going to become now -1, 0 instead of 0, -1. And 0, so the x values are now -1, 0, 2, and then 3. And so when it's a table of values, it's a very simple process to get to the inverse. But when it's an equation, we first have to convert this into a y equals an equation. So it's y equals -4 thirds x plus 4. And the same concept applies. We're going to reverse x and y. So x equals, everything else stays the same. So we have that -4 thirds y plus 4. And when we're doing these, we also need to solve it and get the y by itself because we want it in equation format. So we need to move everything away. So the first thing we're going to move away is going to be that -4, or that 4. And that gives me x minus 4 is equal to -4 thirds y. Now I need to get rid of this -4 thirds. So to get rid of it, I need to multiply by the reciprocal. So I want to multiply both sides by -3/4. So I'm just going to rewrite this. -3/4 x minus 4 is equal to, these will cancel out, y. I need to distribute that 3/4 through to both pieces, or -3/4 through to both pieces. So that's going to be -3/4 x, and -3/4 times -4 is going to give me a +3 is equal to y. And so my inverse function is y equals -3/4 x plus 3. Now let's look at another one. So this time there's a power involved, and I'll show you how you work with the powers. And so when we do these, we need to take and go ahead and switch the x and y. So x equals y cubed plus 8. And we're still going to get that y isolated. So -8 minus 8. X minus... So x minus 8 is equal to y cubed. Now we got to get rid of that cubed. And so what you do is you take the cube root of both sides. And when it's an odd root, it stays just like that. It's just going to be the cube root of x minus 8 is equal to y. And this will give you a graph where it's just basically a s that's been turned on its side, something like this. If you go ahead and type it in your graphing calculator, you'll see a graph, and it has a line that goes all the way from left to right. But when we have something like an x squared, when it's an even power, we'll need to have this plus or minus. So that's only when it's an even power. And so what it will look like is you'll have, here's your original, and then when I graph the inverse, it's laid over on its side. You can, y equals x, this graph line here is you can flip it over that line and you'll have the inverse. So it is reflected over that y equals x line. We know it's 1-to-1 if it will pass both a horizontal line test and a vertical line test. And so I'm going to look at the original equation and, oops, I chose the wrong color on that. Let me choose a different color. Let's choose bright yellow. So the original graph passes the vertical line test. That's the black line that I'm looking at there. Everywhere I cross on it, it passes. So that means it's a function. The next thing is, can it pass a horizontal line test? It can't. So that original function is not 1-to-1. So to be 1-to-1, it needs to pass both a horizontal and vertical line test. So, but if I was to take and break this apart and say, if I was to only look at one side or the other on this graph, would I have a 1-to-1 graph? Well,
I had to call for something else, and I mentioned, did Otto reach out to you about? She's like, no, and then right again, oh, he texted me.
if I looked at only what's happening on one side or the other of this, if I was to only be focused in on the right-hand side or the left-hand side, we could have a restricted our domain and have a 1-to-1. So if I restricted our domain to from 0 to positive infinity, it would be a function, or I could have done from negative infinity to 0. This is the most common way to restrict it, is the positive side, but you could have done either side. So we have a grocery store that pays the managers $20 per hour, and the produce department manager is available to work a maximum of 50 hours. So if we want to write a function that would give the wages earned by X hours per week, it's a very simple equation, right? We have f of x equals how much we earn per week or per hour times the number of hours, and x being the number of hours. So let's find the domain. The domain are the x's, and the x's were the hours. And so the minimum he could work would be 0. The maximum he would work would be 50. Pretty straightforward equation. Let's take it the next step. So again, we're still dealing with that equation, y equals 20x. I want to go ahead and find the inverse. So that means it's going to become x equals 20y. So I need to divide both sides by 20. And x 20ths is equal to y. So that's my inverse function. So we have to go back and think about what is the domain and range for that inverse given the story. So the domain was originally my hours, and the range was my money. What's going to happen is when you do the inverse, those are going to switch. So my domain is going to become the money. So I know at 0 hours, he would be making $0. But if I had y equals his maximum amount of time, which was 50 hours, he would make $1,000. So that was on the original. That becomes the domain for my new inverse function. And the range would be from 0 to 50. Because this was now dealing with our hours. Because the inputs is our money, our output is our time. And this is a function. Because if we graph this, it's just going to be a straight line. This slightly increases as we go. The last thing that we're going to cover is when you have functions and their inverses, the composite of those, that is the one where we did f of, in this case it'd be f prime, or f inverse of x. If this is true, it's going to give me whatever this is will come out here. If I put a 3 here, it's going to be a 3 here. If I put an x here, it's going to be an x here. So let's find out if this is true. So let's find so our original, we're going to put x in for f inverse. So that's already done. And then we're going to plug that into the input. So 1/2 times our input, which was 2x plus 6, minus 3. And I should come up with x. So let's see if that works. Distribute both of those. 1/2 times 2x is going to give me 1x. 1/2 times 6 is going to give me 3 minus 3. And 3 minus 3 is 0. So x equals x. That one did check out. This is how you can test to see if a function and its inverse, the two things are functions or not. You plug it in and do the composite. So would it work also going the other way? So if I did f inverse of f and do the composite of those, I should also get x. So if instead I replace the f function into the f inverse function, so that would be 2 times my input plus 6 should equal x. My input was 1/2 x minus 3. I distribute both of those. 1/2 times 2 is going to give me 1. So x, 2 times -3 is going to give me -6 plus 6. Those cancel out, leaving me x is equal to x. And so it works.